Okay, so I'll give like a little bit of slide, just kind of background. Did is there anyone who wasn't here yesterday for my talk? Okay, great. So you've seen most of the stuff that's on the slide, so I might go a little bit faster. But please keep asking more questions. If you guys don't ask questions, I'll switch to Hebrew. So.
I think by now they know Hebrew.
Okay. Yeah. So I'll tell you a little bit about algorithms, and you saw them, the theorem statement. I'll mention it again, and then sort of for two-player games that we have this Lemke, Hausen, Hewson algorithm. It finds an exact Nash equilibrium in two-player n by n games. Its running time is, sorry, this should be capital N to the n in the worst case, and it means that Nash is no harder than this n of a line problem that we saw yesterday. So this algorithm that finds exact Nash, you can formulate it as finding an n of a line in a graph that's related to the game. So n of a line is it's not going to be NP hard because there always exists a solution, but we don't know anything that does better than 2 to the n time. And okay. So there's this class, like I said yesterday, that's everything that's polytime reducible to n of a line is called PPAD. And finding a polynomial approximation of Nash in two-player games is PPAD complete. And there was a central open question of what happens if you want epsilon approximation for any constant epsilon. Okay, so there's also this Lipton-Markakis-Mehta algorithm, which finds in quasi-polynomial time, it finds like n to the log n, it finds an epsilon Nash, and means an epsilon Nash is probably not PPAD hard. But again, the question was, do we actually need quasi-polynomial time? Is that necessary? Okay, so there is this LMM algorithm for finding an approximate Nash, but there are many other quasi-polynomial time algorithms with a very similar idea. For the same reason, you can reduce the search space to logarithmic. So
you're going to explain it, right?
Is it the LMM algorithm? So the LMM the algorithm is there exists sorry, I briefly explained yesterday, but there always exists a Nash with small support. So there always exists you can only just look at a binary vector with
the strategies of the players can be assumed to have small support.
Yeah. Okay. Yeah. Sorry.
So is this easy?
Yes, it's a Chernoff bound.
Yeah. It's a Chernoff bound. So my favorite way of looking at this is this paper by Sid Barman that talks about approximate Kara-Theodori theorem. So the Kara-Theodori theorem, if you have d dimensions and you have n points in d dimensions, you need d plus 1 points to represent anything in the convex hull. I'll give for example, if you have 2 dimensions and you have any point in the, you can just triangulate any point with just 3 points. If I have anything in the convex hull of these 4 points, like this point, I can just write it as a convex combination of these 3. But this is dimension dependent, and if you want, and you actually need this many points, you need d plus 1 points in d dimensions. But if you're willing to find something that's epsilon close to this, you can use less than you can use less points, and it turns out with when you're doing it depends how many points also depends on the norm, and it turns out if you want to approximate any convex combination of vectors with an infinity norm, you need log n over epsilon squared points. So if you have this matrix and you're doing bilinear optimization, which happens in all of these problems, you can just look at log n over epsilon squared columns of the matrix, and that's the rough idea. And you reduce your search space, and this is all very, very, very high level. But the point is that we have all those algorithms. I'll tell you about the hardness more than the algorithm.
For those who more connected to communication complexity, which is not mentioned here, there is a very early paper of Ilan Neumann showing that in communication complexity, any private coin algorithm can be converted, any public coin algorithm can be converted to private coin algorithm, randomized algorithm, with the additive log n over epsilon squared random bits. So basically they are equivalent. This uses the same, maybe it's the earliest use of the Chernoff bound in the context of matrix approximation. And all of these use the same.
What's the reference for?
Ilan Neumann.
Okay, year or something. Okay. Oh.
One.
Okay, I'll find.
I'll show you. It's one of his results in his PhD.
Oh, okay. Great, thanks. So anyway, there's all these. Thanks, Avi. So there are all these for all these very different problems we have, because they have this bilinear problem embedded. You can reduce the search space to quasi-polynomial search space, and then there's the question of, do we actually need quasi-polynomial time? And again, of course it's not going to be NP hard, because it's so I mean, if you're willing to believe this exponential time hypothesis, it says 3-sat requires approximately 2 to the n time, and then of course all those problems with quasi-polynomial algorithms are not going to be NP hard. I just want to notice this is ETH. It's not strong ETH, so it's 2 to the omega n, and we actually need even a little weaker than that. So this really nice technique of Berkeley repetition was, as at least the term of Berkeley repetition first appeared in Aronson, Pagliazzo, Moshkovitz, and it roughly looks like root n rounds of parallel repetition. And what we get is the reduction size. The reduction size is capital N, which is like 2 to the root n. And by ETH, if you do the math, this is 2 to the n is like n to the log n, like big N.
Reduction between what and what?
So that's right. So the reduction is between 3-sat, and sometimes it's other problems. So we start from typically it's actually a 2 CSP, but you can look at a reduction from 3-sat to any of those problems, and later it will be a reduction from n of a line to Nash. But if the reduction size is this, and you start from a problem that takes exponential time, then you get quasi-polynomial time for the larger problem instance. And I first heard about this technique when I was here at Princeton, well, over there at Princeton 2 years ago, with this paper that by Breverman all, where they get quasi-polynomial hardness for the related problem of epsilon best, epsilon Nash. So it's a decision variant of you want to find the best epsilon Nash. And yeah, since then it's changed my career path, because I've been working on these quasi-poly hardness for many other problems, and it's a really cool technique. Questions on this?
Well, you will show it.
Oh, yeah. So I'm not gonna. So okay, so this doesn't. We don't actually use this, and I'll show you in the next slide why. But it's behind the scenes.
What is a free game?
Free game, thanks. Free game actually doesn't have anything to do with game theory. It's in a two prover, one verifier game where the questions to the two provers are not correlated, are independent.
So you CSP on a to CSP on a complete graph.
Yeah, essentially. So the first thing, if we're gonna do for if we're gonna talk about epsilon Nash, is we have to replace our hardness assumption. It's epsilon Nash is not a decision problem, so we're not gonna get anything for if we assume ETH for 3 set. We need to assume this ETH for PPAD, which says that this n of a line canonical problem requires exponential time. The second thing I have is that almost all of these Berkeley repetition results, they all use the PCP theorem. So they start from gap 3 set, and then they do Berkeley repetition. And it's not clear what is the, or was not clear what is even the analog of the PCP theorem for PPAD. So in a recent paper, we showed that we define what it should mean. I'll tell you later what it means. And
Say the acronyms.
sorry, PCP is
No. The
Oh,
authors. Yeah,
okay.
well, everybody can ask you about different things, but the
Okay.
author names.
okay, great. So this is Babichenko, who's also my co-author yesterday, and P is Papadimitriou, and R is myself. Okay. So we define this conjecture. I'll tell you what it means later. And if you assume assume this conjecture, then you can do the whole Berkeley repetition thing and get this quasi-poly hardness for epsilon Nash. But we don't know how to prove it. It's still open. I'll tell you more later. Okay, let me just briefly mention there are a bunch of other algorithms that try to get this epsilon Nash. So there are a lot of approximation algorithm for relatively large constant approximation. So the state of the art is this 0.33, and it was open whether you can get arbitrary constant. And there are also a lot of special cases. For example, if the matrix is positive semi-definite, then you can decompose it, and then you can sort of do the same, roughly the same idea we had earlier that gave us log n over epsilon squared. Now it gives, when you decompose it, it gives actual polynomial time. Punchline of all of this is
Can you go first?
yeah, sure.
So the PSD means that each of the payoff matrices. What is PSD?
Okay, so I'm not sure. I think definitely if each of the payoff matrices is a PSD, then it works. Most of those algorithms assume something about the sum of the matrices. So,
Positive definite.
sorry?
Probably needs to be positive definite.
Yeah, it's positive. Yeah. So I know for the sparsity and for the constant rank, the sum of the matrices needs to be sparse or to have constant rank. For the positive definite, I'm not sure if they can do it with just a sum, or definitely if each matrix is positive definite, then the algorithm works.
It's something that is natural. I mean, I don't know if
So
any of this is natural.
not natural assumptions.
Yeah, occur in any
Okay. Not off the top of my head. I know that, but so if there was this feeling in the sub community that this full p-test is just around the corner, and people were actually working on trying to get an algorithm. It wasn't all clear that there will be a quasi-polynomial lower bound.
The sparsity, is it it clearly can't be just constant sparsity. So I'm just wondering, is it like a constant fraction?
No, it's constant sparsity.
Also have constant rank, right?
So it's constant sparsity in each column. So you can have full rank, right? The identity matrix, for example.
So like
Yeah.
constant degree graph.
Yeah.
So if the sum of the two pair of matrices is sparse in every row and column, then there's a polynomial time algorithm.
Yeah. And this again uses the same like approximate Theodori, but now you need just the Chernoff bound. You need less than log n.
How sparse is log?
Constant in every row.
Yeah.
It's interesting. It's not obvious to me even in the zero sum case. How
In the zero sum case.
It's not- it's-
Oh, why it works?
yeah. So it's in particular implies right, it's zero.
Yeah.
In particular, it implies a polynomial time algorithm for computing minimums.
Yeah.
So it has to.
Yeah. So I think there is an LP somewhere in the.
Yeah, that is,
Yeah.
But you're saying even in this algorithm, there's
I think in this one, it has to have an LP because just like I said, even if the sum is zero, then you're still solving a minimax, right? So. I know the other algorithms in that paper, and they have an LP somewhere. So. Okay, so like I said, there are all these algorithms, but in the general case, epsilon Nash does require quasi-polynomial time, and the proof uses the PCP-like techniques for the first time inside the class for problems inside the class PPAD. I'll try to mention why it's tricky later, if I don't ask me. But this PCP for PPAD conjecture is still open. You can ask more questions about the theorem statement later.
So, but the
okay.
contrapositive statement is if you have a polynomial time algorithm for epsilon Nash, then you can compute end of the line in 2 to the root n time.
Yeah.
That's
So if we're going to talk about multiplayer games, which we'll have to do today, first of all, there's an issue of representation, because the normal form representation is exponential in the number of players.
so the proof, the result is about 2-player game.
Yeah, but so first of all, it will also go through the result goes through many player games, and also there will be some results for many player else. I'll show you in a second.
In the end of the line, the input is given succinctly, or
Your input in a line is two circuits that compute. You give it a vertex and it tells you what is the next successor and predecessor. So one thing you can ask is about query complexity or communication complexity, like we saw yesterday, but also you can talk about succinctly representable games. So it's going to be restricted classes of games. So the simplest thing you can say, I have some circuit that computes the payoff for each entry in the normal form representation. Sorry, let me get this out of the way. So Another restricted class that's been studied a lot before is this graphical games, and it just means your payoff is only affected by your neighbors in the graph.
That's automatically succinct if your number of neighbors is constant.
Exactly. If the graph is constant degree, then this is succinct. And another very important definition that will come up later is this polymatrix games. You can think of every pair of player playing a two-player sub-game. So it can be like a null, like a trivial game. But I'm playing a two-player game with every player, and there are players. The games are connected because I'm using the same strategy in all of those players, in all of those games. And my utility is the sum of the utility on the subgame. So just polymetrics just says that my utility is additively separable across all those subgames. And again, if I just have this polymetrics property, then I have an n squared representation. I just need to represent all the games and with all the pairs.
And it will be the dimension of the two-player game, the number of strategies in the two-player game.
So n is the number of players. Sorry.
So n is the number of players, but it's the number of strategies.
Okay.
In the game is larger. So n is
Yeah,
the
yeah.
maximum of the two.
So I have n squared times. Yeah, sure. Excellent. But for all our multiplayer games, you can think of them as just 2 actions per player. Oh yeah, the one thing is like I mean if in a general game if you and Ron use mixed strategies but you correlate your mixed strategies, then that can affect my utility. But here my utility is additively separable. So if I only care about the marginal probabilities that each of you play, and that's crucial when you go to 2-player games. Okay, so I had this slide yesterday, but I'll briefly repeat it again. So there's this.
But I just
Sorry.
wonder, the plan of the proof of the two-player game will be that first you'll prove some hardness for multiplayer
Yeah.
games, and then there will be a reduction to
Yeah.
two-player games.
Okay. But there are also results for n players. So. Okay, so you can talk about epsilon Nash. There's a slight issue with epsilon well supported. You can ignore it for now, but just remember that epsilon Nash means that every player is playing epsilon optimally given what everyone else is playing. And we have this more relaxed notion that I've also mentioned yesterday, where epsilon delta Nash, where only 1 minus delta fraction of the players are playing epsilon optimally. Okay, so previously it was known that if you're looking at an n-player game, so Daskalakis, Goldberg, Papadimitriou showed if you have exponential, if you want exponential precision, that's PPD hard, and then Chen and Teng shown for a polynomial precision, that's PPD hard. And in a recent paper a couple of years ago, I showed that even for epsilon precision, that's constant epsilon, that's PPD complete to get a approximate equilibrium for a succinctly representable n-player game. And in this work, we show that even epsilon delta weak Nash, the most relaxed notion, is also computationally hard. And there are also some results about query complexity, but these are all subsumed by the communication complexity that we saw yesterday. Okay, so all of these works were the result was for games that satisfy both the polymatrix games, so the additively separable utilities, and there are graphical games with degree 3 graph and bipartite. The result we have here only holds for just like succinctly representable games, so representable by some circuit. And it would be really nice to get like epsilon hardness for epsilon delta in this polymatrix graphical. So specifically our PCP for p-pad conjecture is that epsilon delta is hard for this graphical polymatrix games. And let me try to convince you that this is why this is natural to call it like PCP for PPAD. So for every player, I have a constraint that I'm playing epsilon optimally. Sorry. For every player, I have a constraint that I'm playing epsilon optimally, and to verify this constraint, I only need to query a constant number of bits. Because epsilon is constant, I only need log 1 over epsilon per season. Sorry, 1 over epsilon per season, so log 1 over epsilon bits. And I only has a constant number of neighbors. So this is really like a constraint and a constant number of bits, and I'm just asking to prove that 1 minus delta of those, finding an assignment that satisfies 1 minus delta of the constraint is PPAD hard.
Assignment now is the strategy.
So an assignment is mixed strategies for all the players, a mixed strategy profile.
We know there's always there are always strategies which satisfy all constraints.
Yeah.
Exactly.
Yeah. Yeah. So this is I mean, this is a special case of finding an assignment satisfies 99% of the constraint in a 3 set when you know there is an assignment that satisfies everything.
Yeah, but there it's a promise and here it's a theorem.
Yeah. Yeah. So I mean, yeah. Of course. I mean, yeah. It's not going to be. It's a special case, right? But yeah.
No,
Yeah. So this.
prove how.
Yeah. This is why I would hope it's PPAD hard, not probably not NP hard. Okay, before I move on, let me just mention that this has other applications beyond. So we originally conjectured this in order to prove this theorem for 2 players, which I'll tell you about, which I'm telling you about today. But it has, if you can prove this, it will have other nice applications for PPAD. If there are no more, unless you have more questions about this, we can move to the whiteboard and I'll tell you a little bit about the proof. Everyone excited? Awesome. Oh, you have Marcus also. Oh, sorry. Oh, okay.
I think we have to turn it to the side.
כן. תמשיכו לשאול שאלות. I'm spoiled.
big glare.
Okay, I can also do this, right?
The other side of the board is actually better condition.
Okay. Can we rotate it? Oh, get away from that. Will it go now? I'm good here. Wow. Awesome. Wow, great. Thanks for spoiling me. Okay, everyone ready for the proof? All excited? Okay. So the way we prove all of these PPAD harness results, there is this what we call the DGP framework. This Skalakis Goldberg Papadimitriou, and we start from n of a line, and then we move on to Brouwer. So we saw essentially this reduction yesterday. I'll say a little bit more today, and then we go to an n-player game. This is something we did not need to do yesterday. And finally, we have a two-player. Okay, so let me start by telling you about this reduction. So if I have a vertex, I have an edge UV in the n of a line graph, I can represent it as a path in 2m plus 2 dimensions. M is the dimension of the n of a line instance. So I'm sorry, I'll somewhere lose track about m's and n's and switch letters. So the way I'm thinking about I want to use these 2m plus 2 dimensions is I think of this one vertex is the current vertex, the vertex I'm in. The next m dimensions are the vertex I'm going to. And this will be I'll first copy. I'll first compute the next vertex, and then I want to copy back from the next to the current. And I have to reserve one dimension for the special op dimension that we used yesterday. No. So this is a computational variant. I'm not allowed to assume that the n of a line has only one line. It has a special vertex where I get a special vertex that has 0, like the special 0 vertex that doesn't have. Sorry.
So what are U and V?
U and V are an edge in the in one of the lines in the n of a line. So they're an edge in the graph. Okay. U to V is an edge in the graph.
So the underlying graph of 0, 1 to the m is a Boolean cube, or what?
So for the talk today, it can be the full complete graph over 0, 1 to the m for today. But up to logarithmic factors, it doesn't matter anyway. So, okay. And now the way I want to embed this, so I can think of my unit hypercube. Let me just draw it in 2 dimensions. I can think of it as partitioned into subcubes. and then I can
One cube is for Brouwer.
yeah. So this is the Brouwer. In the Brouwer world, I'm only showing you two of those 2n plus 2 dimensions. And I can have some walk along the centers of the subcubes. Say if this is a grid graph. And then the idea is to embed the function around the walk. So you saw a little bit of this yesterday, but right on the path, the displacement goes with in the direction of the. Sorry, this is a directed path. So right along the path, the displacement goes in the direction of the path, and when you're slightly further away, you're going into the path.
They are different before.
Okay, yeah.
What is the how is it related to the-
Okay, yeah. So I start with this. I have a say that this is my say that this is my graph. Okay. I will embed this. I will start at u 0 0, and I will go to u v 0 0. So this was a compute next move, and then I have a then I want to switch this bit, so I'll have uv 1 0, and then I'm in copy mode, so I'll go to v 1 0, and then I'm reversing this bit again, so I'm going to v 0 0.
So far you didn't use the up.
Yeah, I'll use it in a second. Okay, but so the path completely ignores the up thing. It just does this from vertex to vertex. This kind of update. Okay. And so, and then once I have the path, I want to create a continuous function whose only fixed points are the non-trivial ends of paths, ends of lines. Okay, and here's how Hirsch and Dmitry construct this function. Right at the path, your displacement is aligned with the direction of the path. When you're slightly further away, you're pointing towards the path. When you're even further away, you're pointing against the direction of the path. Okay, and then when you're really far away, you're pointing in the special direction. This is the up. Think of it as the.
How do you make it continuous?
Okay, so great. How do we make it continuous? So notice that this is pointing with the path, and the next arrow is pointing towards the path. So these are orthogonal. So if you interpolate between them, you don't cancel. So you have maybe like half of this plus half of this. So you still have some constant displacement in each dimension, and you don't have cancellation. If I try to interpolate between the one that's going against the path and the one that's going with the path, then I would have cancellation. I would get zero displacement. It would be a bad fixed point. Okay, but because each layer is orthogonal to the next one, I don't have these cancellations.
But basically, you have a discrete function, and then you interpolate it continuously, or you really define.
So you know, there really is a continuous function.
No, I understand.
Yeah.
But the way it's defined is defined when you say slightly away from the path and farther away from the path. These are discrete distances.
So a discrete distances, and the way it's defined is just between them just interpolate continuously. Okay.
So what happened at the fixed point? How can we see that the fixed point is a fixed point?
Okay,
The line is
Okay, I'll show you in a second. Okay, so just a second. So everywhere else, like so there is something different that happens at the beginning of the path. That's all kosher and nice. But everywhere else, like for example, this subcube that doesn't have the path going through it at all, I'm just going to have everything in the special up direction. So this is what I refer to as like the default displacement. So if the path doesn't, nothing goes to the path, you're safe. Now, if this is the end of the path, then on this end I will also have the default displacement because the path doesn't go through this. And so, and here you have. When you're slightly away from the path, you have the arrows that are pointing towards the path. Now, one of those points that are pointing towards the path is actually above the path with respect to this special up direction.
The ones going with the path, there is no more path.
So
The first layer.
So I want to interpolate. So it's so okay. So first of all, it doesn't really matter what you do in this. You're gonna be stuck with some fixed point. Now I'm gonna just show you one way you can finish this. Okay, so it ends up with a fixed point. But you cannot avoid having this fixed point here. I'm just gonna show you one way to end up with a fixed point. Okay, does that?
Yeah.
Yeah. Okay. Yeah.
A fixed point
Yeah.
anywhere
Yeah. Exactly. So it has to be here, and I'll show you like one way to like end this consistently. So you have a smooth function, and you end up with a fixed point. So define the displacement up to here, define it exactly like we did so far. And then this facet define all up displacement. And between them just interpolate smoothly. Okay, just take the average between this facet and the middle of the cube. The reason you get a fixed point is because of these arrows that point towards the path. So we have an entire subcube, and I can't draw more than that in 2 dimensions. But if you think of the up direction as coming out of the board, then think about the point that's right here, right above the path. It has an arrow pointing towards the path, so it's pointing in this direction. But this arrow, the up direction, is pointing. So this is pointing in the out direction, like up direction, and this is pointing directly down. And when you interpolate, you get a fixed point because these cancel. I'll say it again. So think of the up direction as pointing out of the board. The point directly above the path has to point towards the path, so it's pointing down. But this point is pointing up. And when you interpolate down and up, you get 0. And you get cancellation. You get 0, so you have a fixed point.
So up I understand, but why do you have something to the other?
Why do I have something going down? Okay.
So in
So
this picture it will be down.
no. Okay. No. So I think up and down are a little confusing. So let's rename up as out of the board. Okay.
Yeah.
So
we'll have
so black is coming out of the board, right?
the board.
Yeah. Okay. Now when I'm at distance h over 8 from the when I'm at certain distance from the path, I'm pointing towards the path, right?
So towards the path is now down.
No, towards the path depends on where I am.
Yeah, but if you're
If I'm right above the path, then it's down.
yeah, but if you yeah.
Okay, now I want to interpolate between up and down.
Yeah.
You get 0.
So out and down.
But yeah, sorry, no. So out and in.
To the inside.
No. So think of the point that's right, like that's between you and the path.
Oh, I see. Not above the path.
Yeah. Okay. Think of the point that's between you and the path. Sorry, up was confusing. So it's pointing in, right?
Yeah.
And this is pointing out. And when I'm interpolating in and out, I get 0.
So I want to understand, you're saying all the time interpolate. So you are defining it as the discrete set and then interpolate everything in between.
Yeah.
That's what
Yeah, exactly.
Okay, I see. Somewhere close to the path you get.
Yeah.
Like you won't
Yeah.
get it from the other side of the cube.
Yeah, yeah. It would be somewhere in this, somewhere in this subcube.
Somewhere close to
Yeah.
this. Okay. So what do you do for the source?
Okay, so for the source, let me give you a different like direction of the subcube. So I briefly had this picture yesterday. So you can think of all this stuff as going around this 2m plus 1 dimension, like slightly one lower dimension slice, and everything here is pointing in the now it's actually up.
This is a projection of something?
So this I'm now looking at a different. Sorry, this is the best I can do in the drawing an n-dimensional cube in the whiteboard. But so this is the up dimension, and think of this as another dimension. Okay, whereas this was like D2 and D1. Okay.
Okay.
So now I have sorry for all of these besides the where besides the source, everything is pointing up, and also around the cube everything is pointing up. And here at the top, everything is going to point inside, and here will point down. And this is now we interpolate. And here this goes down and into the into the source, sort of the beginning of the actual path. So this one is actually going, like, the path sort of begins by going down, and then it stays in the 0, and then this stays 0.
Okay, so this is the picture from yesterday where it goes
Exactly.
like this.
Exactly.
From up.
Yeah.
So probably you need to show also that this reduction is like succinct, right? That in each point you can succinctly find.
Yeah. So what you should remember is that in each point, in order to compute the path, well, in each point I can. So okay, this is important. So because of the way I did this, at each point, two of those three remain fixed. Two of those three remain fixed. So in particular, at least one of those vertices is always fixed through this edge. So here I'm maintaining U. Here I'm maintaining both actually, and here I'm maintaining V. Okay. So you can always decode at least one vertex. So you know where you are, and now you just have to apply the previous successor and predecessor circuit to the one vertex that you see, and you can compute. You know where you come from and where you're going to, and then you can locally compute the function.
So you need the path would not like intersect itself.
Yeah, so this you also get this guarantee from this construction, because you always you only have one edge where U is on this side.
That's the reason we don't do UW.
That's the reason we compute then copy, and you always have the two.
Okay, good. So this is the scary picture we always see.
Yeah. I'm glad it's a little more, a little less intimidating now. Maybe, for you at least. Okay, awesome. So Yeah, it's just like keep asking me questions, please. Okay, so what this gets us is it gets us that if you want to find an x, so it's PPAD hard. Can you still see here? Yeah. To find x star such that f of x star minus x star in infinity norm is less than epsilon. Okay, or if you want, you know, like query complexity is exponential. Okay, so
How does the grid depend on this epsilon, like the grid?
the grid size, I think it's like the grid precision is the order of epsilon, but maybe it's polynomial in epsilon for sure. Okay, great. So to go to so this is what we knew before, and to go to the epsilon delta world, we really want to replace this. So this infinity norm means that only one coordinate is changing. So in almost all the coordinates, you're still okay. I mean, if you look at this, the displacement is only in only one dimension. So in almost all the coordinates, you're okay. So you're not going to get hardness of approximation from this. So what we want is we want to replace this infinity norm with 2 norm.
Can you explain why you do the different?
So in the it'll make more sense when you see the next step in the reduction. I'm just a little short on even with this fancy whiteboard. I'm a little short on space. But okay, yeah. But let me just tell you now that here you're okay in all coordinates but 1.
Okay, means what?
So you're fixed. So so f of x minus f x star minus x star is actually it actually looks like the fixed point in all but 1 coordinate. So in other words, your displacement is only non-zero in 1 coordinate. So in all but 1, you didn't do anything. So it looks almost like an equilibrium. And
in fact, everywhere it looks like that.
Everywhere looks almost like an equilibrium, exactly. And what we want instead is this to get something in 2 norms. So in a constant fraction of the coordinates, you're constant far from.
So you're saying that if I just pick a vertex that is on the path here, I'll get something close to an equilibrium.
Or even not on the path, even here.
In L2 norm you will. Not
Yeah.
In L infinity it will be far away. It will be epsilon away. But in L2 it will be.
So
If
it's
you're
like you're saying the other.
Oh yeah, sorry. So it's tricky because we used to think of L infinity is larger than L2. So this is like a normalized L2. So there is some I want some epsilon over root n or times root n or whatever is the. You need to somehow normalize by the dimension.
No,
Okay,
but,
I'm hiding it.
intuitively, if you forget one dimension, the right dimension at every point, then you are a fixed point. Because no dimension changes except for 1.
Okay, you're saying that every point here is close to a fixed point in the sense that if I delete
Yeah,
one of the dimension,
exactly.
it will be a fixed point
Exactly.
of a new function. This is somehow bad.
Yeah, because so intuitively, like my intuition is that it's not going to be hardness of approximation. We want a constant fraction of the things to be wrong,
So you want
like a constant fraction of the constraints to be
non-fixed points
unsatisfied.
to be like really
Yeah,
non-fixed in like
yeah,
any of the
in a
dimensions.
constant fraction of the dimension.
Okay, and then you have this normalized.
Okay.
So this is the PCP aspect. You want to
Exactly.
move from one violated constraint to many violated constraints.
Exactly.
Okay, so this is why the 2 is crucial here, but wasn't crucial for the communication. Where you
So in the
also cared
So in the communication, to get the stronger results for like to get actually hardness for epsilon Nash for 2 players, you also need this too.
So what do you get if you don't use infinity
You get hardness for like a weaker. I think
Don't you get just
So-
polynomial?
it's a little different when. I think in Omri's paper it's something like 1 over polylog. I don't. There is a question of what's n there, and
So you won't get it for a constant epsilon, you'll get it for
yeah.
like a different epsilon.
Okay, but getting this like constant as epsilon is actually, in hindsight, it's actually much easier. Like this 2 norm is actually much easier than it's like a 1 line. Okay, So-
One line to do what?
to improve from infinity norm to 2 norm.
Oh,
I mean, it's going to be 1 line on the board. It's like a few pages in the paper. So error correcting code. Actually, it's 3 words, right? Okay. So I'll encode this with an error correcting code, and this will just do a redundant error correcting code. I'll use m prime. Yeah, just repetition.
Yeah, so this makes sense. Now if you differ on 1 dimension, you differ on 3 dimensions.
Yeah, exactly. So, yeah. Yeah, and now we get this 2 norm.
Yeah, but you don't get all points in space this way. The error correct.
Yeah, okay, exactly.
You find it outside the image
Oh,
of the-
awesome! Exactly. So, thanks, Avi. That's awesome question. So the main sort of I think one of the main obstacles for doing like PCPs and error correcting code, etc., for problems in PPED is these kind of problems is like, what do you do with points that do not look like the error correcting? They're far away from the code. And the answer is that up. Exactly. We have this default dimension, so anything that's far away from the error correcting code, you just do the up.
But now you do up in many directions.
Yeah. No. Yeah. Now I'm doing up in m prime directions. Okay. So the points that are really crucial to remember from this are that we have this up, and we can locally compute the. Okay. Let me erase most of this.
So is up and different 1 more dimension, or
So after I do the error correcting, I need the repetition code for the up to be. Yeah. Okay.
for the
Yeah.
reduction between end of line and up is just a dimension, or
Yeah, it's an extra dimension.
it can be up?
No, it's a special dimension. That's yeah. So the path never goes in the in that dimension. Okay, so we have. Let's remember this 2 here. And now I'll show you the reduction from Brouwer to n-player. And you've almost seen this yesterday, so we're kind of familiar, but now it'll be with n-players. So it's essentially this imitation game that we saw yesterday. So I have, actually I'm going to have 2 n-players. So there will be n A players and B players. And for the each of them will output each of them will output a number in the continuous interval. But you can actually reduce it to like binary, and it's all.
Binary
Sorry.
in discrete.
Yeah, discrete. Yeah, sorry. Boolean. Like actually, there is a variant where each player only uses 2 actions instead of infinitely many. But for now, let's think of it as infinitely many. Okay, so the cementation game that we also saw yesterday, utility of the ith A player when she plays xi and the jth and the ith B player plays yi is just minus xi minus yi squared. And again, because of this, this breaks into the variance over yi and the expectation over yi, so she only cares about the expectation of yi, and everything's nice. And for the jth B player, it's going to be minus the jth component of f evaluated at x minus yj. Okay. And every approximate equilibrium of this is an approximate fixed point, and because we have so now every player corresponds to a coordinate, and because we are far from equilibrium in delta fraction of the coordinates, we have that like we get an epsilon delta hardness for epsilon delta Nash equilibrium in a succinctly representable game. Okay, so this already gives hardness for epsilon delta Nash both in the like computational setting and the query setting, and as I say also the communication setting. In the communication setting, you have to do something different, right? You have to do this all protocol. Yeah. Yeah. Okay, but the problem with this game is that in order to go from n player to 2 player, we need a polymatrix game. And this game is totally not polymatrix. So remember, polymatrix means utilities are additively separable. But here, BJ's utility depends on the entire vector x at the same time. So if you're used to thinking about CSPs, this means this constraint, I have a constraint on n variables, which is terrible. Like we can't.
But actually, the way f was.
You need to lose something, right?
Okay, well, sorry, one at a time.
It's expected that you would lie into trouble, otherwise you would prove to lose and no more.
Exactly, right. So this would be first of all. So we also need to do like a birth repetition at some point anyway.
Why
I
are we
thought
going
that this is the point. Okay.
No, okay, yeah. So this is the point we will also need to do birth repetition at some point anyway.
Why are we going to n players?
Okay, great. So yesterday we could do 2 player, but we just had like Alice and Bob, and Alice just picked a vector in 0, 1 to the m, and Bob picked a vector in 0, 1 to the m, right? But this means their strategy space is exponential in the dimension of the cube. So it was okay for communication because all we hope to show is polynomial lower bound.
Yeah, okay, so this is because you're okay, because you're
Right? I want the strategy space to be smaller than exponential. So in the communication setting, I
these 2 players with n strategies.
can use 2 players with n strategy, but in terms of what we did yesterday, so what we did yesterday, we had one Alice player that had a vector in 0, 1 to the m, right?
Yeah.
So her number of strategies, even after I discretize, her number of strategies is exponential in m. And I'm sure I have a lower bound that's exponential in m, and so that means I have a polynomial lower bound in the communication complexity. But for computational, I want stronger than polynomial. So I need the strategy space to be smaller. So I can't if I have 0 like exponential strategy space, it's not going to give me anything for computation. Okay, so that's that.
And then that's the reason you use n players.
That's the reason we're going to n players, and then we want to we'll go to 2 players later. And Avi also had a question.
Well, just that itself is defined sort of locally. It doesn't use all dimensions.
Yeah,
The arrow code.
yeah. The error correcting code, but also F. So the other thing is that F also has the successor and predecessor circuit in it. So that's already all the dimensions, right? Because they input it. Okay. But
But you were saying that the originally. So what is separable now?
so
This should be separable.
so right.
Okay, so why did you say
The A is separable. The utilities for A are
Yeah.
defined locally.
Yeah.
But here the utilities for B are
Yeah.
okay. So let me tell you that I need separable now. I'll show you the.
So you just need separable to have few strategies to have
No, I need the utility to be I need like each players to be utility to be additively separable.
because you want the domain to be small.
No. So yeah, essentially. So in other words, the reduction from n player to 2 player, I can tell you to you now. It's very easy. Alice controls these players, and Bob controls these players. So the Alice's mixed strategy is pick a random player and say what's the player for this strategy. What's the strategy for this player? And Bob will pick a random player and say what's the strategy for this player. When I'm
Play the little game.
yeah, and they're playing the little game between them. But here so when Bob only sees one player of Alice every time I'm evaluating the utility. Bob cannot just look at all the players of Alice because that's again exponential. So that was very hand wavy, and we'll come back to that later. But the punchline is I need additive separability. So our goal.
Why you need it in the reduction, but you kind of knew you needed it because you needed a small space to not.
Yeah, exactly. I mean, it's a sort of the same thing, like two sides of the same coin. But our goal from now is to get a local f. So a local hard Brouwer function.
Can you say that when you like bird that?
I'll essentially, but eventually that's what it will mean, but not at the moment. Okay, so the first problem, before we even talk about error correcting codes and whatnot, which is already like you don't expect it to be local because it's an error correcting code, so there's something weird happening here. But before we even talk about that, the end of a line problem is not local. So I want to define so sorry, we're not here anymore. Now we're here. So you have an arbitrary circuit from n inputs and outputs. There's no reason an output should depend on. Right, okay. So let me define a new problem. Local n of a line. And here's something that could be really nice. So use red. So here's some wishful thinking. Suppose instead of arbitrary S and P circuits, successor and predecessor circuits, I could have successor and predecessor circuit, and they belong to NC0. So this is the class no one ever talks about because it is essentially meaningless for a single output, but it means that every output only depends on a constant number of inputs. Furthermore, I want the requirement that if I compare, I have some vertex U, and I compare it to its successor, I want to say that its Hamming distance is order of 1. So I only change a constant number of bits from every vertex to its successor or predecessor. And every output bit only depends on a constant number of input bits. So, extremely simple circuits, right? So we don't actually get this, but let's say
Oh.
You're almost
Yeah,
on
I
the
understand.
you're almost on the Boolean cube, and this function is computable by an S0.
So
In
now
the
we
Boolean
change-
cube, you are allowed to change only one bit, right?
Yeah.
He's allowing you to
Yeah.
change a constant number of bits.
Okay, and you want this to be
And-
P-pad hard or something?
Yeah. I want this to be PPD hard. Okay, so we actually get almost this, surprisingly. But okay, first of all, let me tell you why this is good for anything, and how do we get around this like error correcting code issue. So say that E is a linear error correcting code. Okay, then so I have this point. I want to know where the path is going. So I have okay. So if E is linear, I can write the encoding of S of U, right? That's where this path is going to, is equal to the encoding at U plus the encoding of S of U minus U.
No, this is small.
And this I can locally access because it's part of the point here. And this I only need to read a constant number of bits to compute this. So I can do this, and then I add them, and then I there's the okay. So like I said, that I can almost do this. I actually don't know. I mean, I don't know. I don't know to prove that you cannot do this, but here's what I know you can to prove that you can do is almost this. But now instead of operating on the entire hypercube, you're operating on some subspace of the Boolean hypercube. So all these guarantees are okay as long as S and P take as input a vertex that belongs to the subset V. And verifying that U is in V is actually in AC0. So I just need one really large gate, but otherwise everything is still local. And this means sort of that you can use, without lots of generality, you can use AC0 circuits for PPD. Because if U is not in V, you can just have a self loop, which is allowed.
What is this
So-
thing
so-
now? Why do you need it?
So,
To show that it's
no.
These properties, the first two properties will hold only if U is in
Yeah.
and also the whole path will live in this subspace.
Yeah.
Who is V?
So V is some subset of the hypercube.
But why do we need it to hold only for a subcube? For a
Because the
subset?
path will live there, and you don't.
So I don't know how to prove that this is PPAD hard
Oh, okay.
if they're applied for the entire
So
hypercube.
this is just easier to show.
Yeah. This is what I can do is this.
Okay.
So these hold, but as long
Like you need it, it's not like you wanted it. You just
Yeah.
can't show it.
Yeah. Okay. So this is
And this the V will be the tunnel.
yeah. So it's not exactly the tube because this is still in the discrete world. We're not talking about bar at all right now. This is all in the discrete world. But even in the discrete world, I'm going to throw out most of the vertices for completely different reasons. Yeah.
So the dimension of V will be root time.
No, it still has to be exponential. No,
No, so
I mean, yeah, V
V is linear.
yeah. Because it still has to be exponentially hard, right? Okay, so this is great, right? We have everything.
So this AC0 circuit, this can only happen if this is such a low density parity check code, right? I mean,
It's I have one large AND gate. That's it.
No, it's n-gauge of parities. This is a subspace to verify that the
No, it's sorry, it's not a subspace. V was
subset.
subset. Yeah.
Oh,
This is the wrong. Sorry.
Subset.
Yeah, this is a V is maybe a bad letter. But, it's a subset, not a subspace. Okay, but so it's this really simple thing, but
No, wait a minute. Why is it okay to if it's a self loop? Oh, it's the end of a line. You want to find
Yeah.
the end of starting at
yeah.
zero. Here it's not.
No.
No,
It-
self loops are very
self
bad
loops-
for functions in Brouwer.
Oh yeah.
End of the
Yeah, I mean, you can think about it instead of a self loop. If you can think of having like two copies of the graph, and you're going here and you're going back, so you have a circle. Okay, but of course, so AC0 is a super simple class of circuits, but we are not local anymore.
You are not local for verification, but you need locality for this property.
Yeah. So I mean, if I give you a vertex to compute the next one, you need to know if it's in V or not, and that's not not a local operation anymore. Okay, and here comes my favorite part of this proof. It's stuck. What do we do next, right?
You use random restriction.
PCPs. So I concatenate this array correcting code. I'm gonna add a PCP. So pi is gonna be a PCP for the statement that U is in V.
So what did you do with the dimensions?
So I increase the dimension a little bit. PCP is by itself also an array correcting code. So my encoding will be this E of U, where it's important that E is a linear array correcting code for this trick, and I'm going to add a PCP. And then I can, with this PCP, I can locally verify that the V is actually in the AC0 circuit actually is what we want it to be. Okay, I want to tell you a little bit about the PCPs. How am I doing in time? What's that?
40 minutes.
40 minutes, perfect. So this is going to be I'm not going to use it anywhere that's AC0. Might as well be NP. So the construction of the PCP, there is nothing fancy going on in the construction. I'll give you a high level view in a second. The hard work is proving really weird properties. They're not hard to obtain. Just no one considered those properties.
Again, what are we trying to do?
Okay, so now I'm constructing a PCP with some very strange properties.
Really, this is the reason we need to construct the PCP. Just
Yeah.
because you needed the set as an
Uh-huh.
artifact.
Yeah. Crazy, right? I don't know how to go
Why
around.
is that PCP in the paper?
Well,
Seriously, this is the only reason?
Yeah.
Because you couldn't show that it's...
yeah, okay. Awesome question. Yeah. So, yeah. This is the only reason. I just want PCP in the paper. So my intuition, I've only been working on this one for a few years, but my intuition is that you need a PCP somewhere. And sort of when I saw where this PCP was coming in, I was like, okay, now I have a PCP, so like.
Is that sketchy?
No. If I didn't have a PCP, yeah,
Sketchy.
it's less sketchy. Yeah, exactly.
So do you know that it's not hard if you go over, I mean...
No, I don't know. I mean, maybe you don't need this like subset V. I have no idea.
Maybe you can work harder and
Yeah.
the subdomain, the subset V?
Yeah, maybe. Yeah. I mean,
Okay.
yeah, I'd be very surprised if you don't need some PCP like something anywhere, but maybe you can.
This is the only place.
Yeah.
Why not use zero collective codes?
Yeah.
I don't. Okay, I have some like informal intuition. Like maybe I can formalize. Like I don't have anything formally. My intuition is that there's still a hardness of approximation. That sort of. And I haven't haven't seen any. So it ultimately it's a hardness approximation for a game. So I don't have. So the final constraints are not local. But I haven't seen for any of the related problems. I haven't seen anything that goes without PCP at all. It doesn't mean you cannot. I haven't seen and we get it for free typically, so we don't care.
It can be a goal in itself to have a game which is locally defined, right? Where the payoffs are locally defined. That is hard to approximate. But
Yeah, I'm not sure. Yeah.
for this kind of goal, it seems maybe natural to have some kind of this.
Yeah. So yeah, I'm not sure. I'm not sure the
Set,
The set V.
other set B. Maybe there may be
Set
yeah.
V. But probably we need to see the reduction for this.
okay.
People
Yeah.
Okay.
Yeah. Let me tell you a little bit about the PCP, and then we can go back to whether it's needed or not. We thought, like, irrespective of the final result, I think these are some cool properties of PCPs that people haven't looked at before, and yeah. So, okay, last time I tried to give this talk, I first wrote a list of the properties, and then I got really I got some angry feedback. So your PCP is so simple. Why don't you show the PCP first and then show us the property? So I'll give you a 5-minute proof of the PCP theorem. Okay. There's going to be a lot of lying and hand waving. Okay.
So this is a proof of what?
This is a 5-minute proof of the PCP theorem.
Your PCP? What PCP?
So what I'm going to show you now is it's like a long line. It uses a lot of papers. I'm not going to start listing them, but specifically what I'm going to show you now is like it uses a notation from Polishuk-Spielmann 94
This
or
is
95.
PCP for NP?
Yeah. PCP for NP. Yeah. Forget about the AC0. AC0 is just a cool
So this
artifact.
Okay, now you show us the PCP theorem.
Yeah. I'm going to show you the PCP the proof of the 5-minute proof of the PCP theorem the way I look at it. Okay. So I need a finite field G, and I need a subset F in G, where F and G are of size approximately square root of n. Okay. And now I'll take my I have my circuit, which is it can be any P circuit, but in particular it's AC0, and I have some assignment, and I'll write them as a polynomial from F squared to G. Sorry. So there is some encoding of the circuit assignment as a polynomial from F squared to G. Okay. And now I need the error correcting code. So I'll think of oh, sorry, and this circuit and assignment. So, and this is satisfying. The assignment is satisfy. The assignment satisfies the circuit if and only if phi equals 0 over if phi is equal to 0 ever, then this is a satisfying assignment. So now I'll have a capital. Sorry, this is a. Okay, so I'll have a psi. It will be low degree extension. So C goes from G squared to G. And when I'm saying low degree, it's the size of F, so approximately root n degree, but smaller than the entire field. Extension of phi, yeah. And now my goal is to locally verify that phi is 0 everywhere in F squared. So
The line
exactly.
So degree, probably 2 times that.
It's individual degrees F. I'm skipping logarithmic factors, so don't get me on the constants. No, yeah, I'm kidding. Okay. So I'll define this polynomial C prime of x and y. It's going to be the sum over fi in F of C of fi, and I take I to the y to the ith power. And so this is a sum check or zero sum check, something like that, right? Sum check protocol, right? Is that, or zero? No. Okay, there is zero check. I don't know what's zero sums game theory. Okay. Sum check protocol. I think that's what it's called. J y x to the j. Yeah, so C double prime does the same thing with C prime, and I replace I replace the f x and y, the roles, and the reason this is good.
These are just the projections of the original polynomial on the rows and on the columns of the. The restrictions, sorry.
No, exactly. So this is the. This is a new polynomial. Right, I have C of xy is C of x and fi times y to the ith power.
Fix one coordinate.
I fixed one coordinate, yeah, but okay. And
the original polynomial that it should be thought of, I mean, if I understand your notation, is phi of f1 or fi, fj, x to the I, y to the j.
So, what you get here, you get the C double prime of xy is the sum of fi of j, C of fi of j, x to the j, no, this is j and this is I, x to the j times y to the ith power. And all of these are only degree f, so they're all low degree in each variable. Yeah, it looks weird. I don't have Avi and Ran probably have much better intuition for why you do this than I do. The punchline of this whole thing.
It's also a small phi fj fi, right?
Yeah.
Can you expand it simplicity?
Yeah. I'll like give me 2 more lines and then it'll look familiar. Okay.
It's similar to subject, but not exactly the usual
Because
the
there is
definition of subject.
there
but
is
it's
1 to
similar.
the I. What is 1 to the I?
Yeah, it's
It's-
just a different way to do that,
Okay.
which is
Okay.
kind of similar, but
You
plays the same role, but
Just put the values
not
on the
exactly
coefficients of the polynomial. That's what you were saying.
Yeah, I understand. It's getting new polynomials for some reason.
Okay.
So, in the, you have a bivariate polynomial of low degree,
Yeah.
and you are getting its values, but they are wrong in in some constant fraction of the entries. Think of it as a big matrix.
it's
And
a
you want to
different
tell-
way to present it,
Okay.
but it's
L-
similar to subject.
Yeah, I
in
see that
nature.
it's somewhat
Let me get to the point. Let me give me 1 more line and then I'll try to tie it all together. Okay.
I think it's worthwhile. I mean, there are people maybe who never saw any PCP anywhere, or this.
Yeah.
The type. What?
No,
You want to check?
I have never seen a PCP.
There you go.
Yeah. Thank you. Okay. Awesome. Let me finish this and then
Almost.
I love the questions, but
Yeah. They will change their
Almost easy, so almost
No, like I
easy.
think people took Sanjeev's class and he's like,
So
Gilad.
it's a very complicated way to say that you are taking the values and encode them.
there is a reason I'm doing this. Okay.
yeah.
Bear with me 2 more minutes and then show me how to simplify it. Okay. So the psi double prime is the 0 polynomial if and only if this holds. Okay, so this is the whole magic and the reason we raise powers and whatnot. So you can see that if this is if phi is 0 every 1 f squared, then this is just evaluating phi everywhere with all the x, j's, and
So in the
yi.
prime you need phi, right? Yeah, you have phi.
It's
No,
the same because it's
psi and
no, in the summation should be phi, not psi.
no, because you're evaluating on x, y, where x can be not. You still want.
Oh,
You,
sorry,
yeah.
phi was defined from C.
Yeah, and you want psi prime and psi double prime have to be still low degree polynomials, so you can so they're error correcting. Now, the punchline of this whole thing is that first of all, it's error correcting, so you can make sure these are actually defined correctly by only checking them at a constant number of locations. And the second thing is that to verify like each location is defined correctly, you only need root n queries. So you can use root n queries times constant to verify that psi prime was defined correctly from psi, that psi double prime is defined correctly from psi prime, and that psi double prime is 0 everywhere. Okay, so in root n queries you can verify that phi is 0 everywhere in f squared, so you can verify that the
so the proof is C prime and C prime prime.
so the proof is psi prime, and psi double prime. And so these are all error correcting. And so this gives you a root n query PCP. And if you want so that's all we need for, we will only have a root n query PCP. We're not going to go beyond this. But to get a constant query PCP, you just recurse, where recursion. So you sort of do this, so this is again an NP statement. You can recurse off the off topic. So this is all you need to know about PCP theorem.
Well, it probably will not be constant, it will be logarithmic if you recurse it, Degrees will go up.
Somehow you can recurse and get constant. This is beyond beyond what I know. I know the final theorem statement is a constant number of queries, but
Using this way,
Stuff.
this way,
I don't think it's going to give constant, at least with the standard reductions.
okay.
With the standard Gaussian.
Okay, so maybe
That's
there.
all you need for the
Anyway, I think okay. I stand corrected. Anyway, I don't know what happens after recursion. For our purposes, this is all we need, and sort of a very super hand wavy. Maybe if you could somehow recurse what we're doing here, then you can get this like PCP for PPAD. I don't know. I have no idea how to recurse this for our purposes. Okay. Let me tell you about some crazy properties that this PCP has. So first of all, it's root n queries. It's not crazy yet, but this is okay. The second thing is so the PCP would typically the two parameters most considered are the number of queries and the number of queries bits we're querying, and the random bit complexity. So the random bit complexity here is 1/2 log 2 of n random bits. So even if you want to find even when you want to query one bit at random, that's already log n random bits. But because we're bundling up root n queries, picking a random root n tuple from if you have a root n partition, picking a random root n tuple, you only need this many bits. And this is actually necessary because the final reduction size is going to be doubly exponential in this. So it's crucial that we get half log n. We use all the pseudo randomness and whatnot.
So again, why half log n?
So if you think the best thing you can hope for,
To pick a line or
Yeah.
or a column in the matrix.
to pick a random line, you need half log n. So this is like the best thing you can hope for, and you use like pseudo randomness and stuff to get this.
You need the log degree tests also.
Everything you can.
The same.
Yeah. Use pseudo randomness for there's some I don't know whatever approximate y's independence and whatever. Low bias sampling, etc. Am I even in the right paper? Yeah. Okay, so something else that okay, if you think that this was, let me show you the real really weird property. Okay, and then you can it's something I call local proof construction. Okay, what I mean by this is that okay, what's our final goal, right? We remember want to compute the next want to compute f locally, so we have to compute the next this locally. So it's not enough. So here we can do this trick and we can get the encoding, the linear encoding of SFU locally, but our PCP will never be a linear correct encode. So I want to be able to look at the linear. So this is like really a holographic proof. I have a specific encoding. I'm looking at the linear error correcting code, and looking at this linear error correcting code, I want to locally construct the proof of the PCP.
So you want an NC0 conversion of the PCP for.
Not. So here locally is root n locally. Okay. And so first of all, it has no way to work with less than root n, and let me show you how it's possible with root n.
So what do we want? We want to compute.
I want to. So if I give you local access to this error correcting code, I want to locally construct the PCP for the successor. Yeah. So this C is actually a linear error correcting code. So we actually get this. You can locally access psi. And in order to construct psi prime, you need to know psi on one line, on one row or column. So that's only root n queries, so that's still okay. In order to construct psi double prime, you need to know psi prime on a row, but that's not okay because psi prime is not linear, right? So we cannot construct psi prime, psi double prime.
You are not pointing to the right.
Oh, sorry.
You want the, you go.
No, this is psi double prime. So I can
Double prime is just a column, no?
no psi prime is a column of is a row of psi. Psi double prime is a column of psi prime. But psi prime is not linear. So it's like n axis n queries to.
That's different than Spielman. For them, the columns are not defined by the rows. You don't. There's no need for that.
So these lines are copy paste from Spielman, but let's we can take this offline. You know I'll take the credit, sure. Anyway, the point is that we get this for psi for free. We get psi prime locally. We cannot get psi double prime locally. And this is the point where I had like a mini crisis. I was depressed for 2 days, but it turns out you just don't need this. So if you have psi prime, you can just locally verify the psi double prime is 0. You pick a point of psi double prime instead of the proof the prover giving you psi double prime, the prover just gives you psi prime, and you can locally verify that the sum over a column is 0.
There are many columns.
Yeah, you pick a column at random, and because psi double prime is error correcting that. So this is this weird local proof construction. Something else, again, we get for free, but I don't think it's been considered before, is a tolerant PCP verifier. So in PCP, typically, if you get a proof that's actually a proof, you have to accept. If you get something that's far from a valid proof, you have to reject. But here I want to say that even if you get something that's close to a valid proof, then you have to accept. So it's similar to like tolerant testing and property testing, etc.
By the way, it's all probably a PCPP,
It's related. It's related. I'm not sure exactly what's the. I borrowed from that paper as well. And this line next time will be even more related to PCPP. So there is what's called robust soundness. So robust soundness, the way I look at it is the verifier picks some, tells you what is she going to query, what bits of the PCP she's going to query, and then there is an adversary that can corrupt the constant fraction of those bits. And then the adaptively corrupt the constant fraction of those bits, and then the verifier gets to see the bits. So this is robust, and you still have to be sound with respect to this. So here I want robust everything. So this tolerance property is robust, and there is a local decoding which is also robust, and everything is robust. And again, you get this from free from existing machinery, but just it's a cool property to note. Okay, with all of this, then we can actually use this trick to compute the next U locally. You can also, because of the local proof construction, you can also compute the next PCP locally. And now F is root n local.
And this is a root n that comes in the.
Exactly. How am I doing in time? Oh, there's a clock here. 12 minutes. Perfect. Okay. Okay. Yeah. This. Okay. I'll go slightly over, but not much. This is almost it.
Well, the summary is that you can make the path construction, this reduction, to Brouwer in a way that the function successor and predecessor are root and local.
Yeah. Okay, so we achieved this, and now let me show you this again. It's going to be a little different this time. So okay. So theorem, I have a polymatrix and bipartite game with root n players and 2 to the root n actions for each player. And that's as hard as n size. So I have a reduction to like this. Yeah. Okay, so again, I'm going to have like A players and B players, and I have a root n of h, and the A players correspond to PCP verifier string questions, or the random strings of the PCP. So these are the sort of like the answers to. So each A player tries to give an answer to a question of the PCP verifier. So remember, I have root n queries, so I need 2 to the root n bits to answer the query, and so because of the randomness was half log n, I get root n players because they're. And the B players are going to be just like a. I think you can say random. It's of the coordinates. So it's not actually random. It's actually orthogonal. So you can pick it in a way that's completely orthogonal to the questions the PCP is answering, and so the intersection is always, the intersection is exactly the right size that you want. And now the so if you have this game between AI and BJ, so AI is incentivized the same imitation game type stuff, incentivized to copy bits in the intersection. So they each have root n tuples, and they have exactly the right number of coordinates. And by Berkeley paradox, and BJ verify AI's answers locally compute. If and then imitate f of x on intersection.
So it's a full bipartite graph.
Yeah.
Every I and j up front.
Okay, so I can erase everything, but let's see. Okay. So we got like the n player where we have its polymetrics like we wanted, and now players. And now this from root n player to 2 players. This is completely standard techniques.
Just breaks the to the root and strategies too.
Yes. So so Alice picks a random A player plus strategy, and Bob random B player plus strategy, and there is a gadget due to Althofer that forces them to play approximately uniformly at random. So this log n over epsilon squared support is tight by this gadget, and I mean, I'm not sure about the epsilon, but the order of log n support is tight by this gadget, and we actually use them to have large support. So they're the random A player and random B player, they're actually choosing them approximately at random. That's it.
So can we go over the chain and see what we got? So
Okay. Okay. So instead of n of a line, we had this local n of a line.
It's hard. In itself, it's an end of a line
What-
game.
what
You
is
want to
the-
start
what
from
is
end
the-
of a line. You want to get to the layer. It's
hard to get
yes.
Okay. So we had we changed this to the local n of a line.
Where is the n to the log n?
Okay. Okay. Right. So our reduction size is 2 to the root n, right? Because each of these players has 2 to the root n actions, and also we want Alice to pick a player uniformly at random. She has root n players, and this gadget is exponential in the number of things you're randomizing over.
Okay, so let's say everything again. So local and flan, you show that it's P-pad hard.
You assume.
You're assuming that.
Assume it, and then
No.
some other problem is
No, no.
capital N to the capital.
No. So
No,
capital N.
this you
local n of a line is PPL hard with this with the
Yeah, I mean ETH.
no.
You
No.
assume ETH for it.
Yeah, okay, hold on. Okay, let me. Okay, let's go over this again. Okay.
I think Aviad will be simpler if you show that the polynomial time algorithm for 2-player or to approximate Nash for 2-player will give you 2 to the root n algorithm to the original end of the line. That's what you did.
Yeah. Oh, okay, so let me do this again. Slower. So we started from n of a line. Okay, and then we reduce to this local n of a line problem with v, this annoying subset that we have to. Okay, then we got this reduction to Brouwer with 2 norm, but now it's also local with PCP and everything.
and this is like a normal reduction, polynomial
So-
what?
I never actually wrote a theorem statement for what local Brouwer means. I don't have a good formulation for what this means.
Okay, but this reduction is polynomial time.
So I mean, so the reduction from to just to Brouwer is polynomial time,
Okay, good.
and then we're going to this like root n player 2 to the root n actions. So see, this is a blow up of like sub exponential blow up.
Okay.
And then from here to here, this is polynomial in the 2 to the root n.
Okay, so end of line was.
End of line.
Okay, so what we got is.
N of line was in n dimensions, right?
Yeah, I mean the description size is n. Yeah.
So if you assume the end of line is 2 to the n hard, then
Mm-hmm.
the last problem is like something else because it has like the input size is 2 to the square root n, right?
So
it's not n hard, but the input size is 2 to the square root n. So that's why you get this n to the square root n. That's the only reason.
This is if capital N is the size of the matrices in the two.
yeah.
So what about
The two planes.
the Russell and Scott and Dana's work? Where is it?
So, awesome. Thanks. How does this relate to birth repetition? Awesome question. So there is all these other works, including like Aronson and all. They get quasi-polynomial hardness for related problems. And what they do is they start from you start from a 2 CSP, and then for which you have a PCP theorem, and then you bundle up root n queries. You bundle up root n queries, so really you're getting a root n query PCP with lower randomness.
And you're claiming that you're doing the same.
I don't know. Instead of going through the PCP theorem with recursion and then bundling things up, here I'm going directly to. I'm staying in this root n query. I never go to like constant query and then bundling up.
Yeah, but they're doing computational problems and you're doing total functions.
But potentially they could also, instead of, if they didn't know how to prove the PCP theorem, potentially they could also just use this like root n PCP and get the same hardness result that they get anyway. And I sort of do this in a paper about like detecting communities, where
So
that's.
you don't take anything from their paper by the approach.
The only thing that I take is like, let's do a reduction of this size. But
And can you talk about the ETH for PPAD? I thought that people don't believe that PPAD is like NP hard.
Okay. So
The N hard.
I thought people are
okay.
PPAD is somewhat easier than
Let me. Okay. Okay.
but still the equivalent of NP or something.
Okay. Okay. Here's my answer to this. What is ETH for PPAD really a reasonable assumption? I will not be completely shocked if you told me ETH for PPAD is actually false. Well, first of all, I only need like 2 to the n to the 0.51 is enough. Instead of like assuming all the way to 2 to the omega tilde of n, if you just have 2 to the n to the 0.51, that's enough to show no poly time. No, and the second, I will not be completely shocked if you told me that ETH for PPAD is false. I will be very surprised if you told me that ETH for PPAD is false, but ETH for 3 set is true. Here's my
Don't think that
Really?
PPAD and
Yeah.
NP are that PPAD
Okay. Here's the one way I look at it. Okay, I give you a circuit, and I give you a black box circuit. Can you actually do anything useful by knowing the gates?
But it's not really just a circuit. You give a circuit that can really
Okay, sure.
can invert.
True.
easily.
If you have
That's
only
the
one
main
circuit,
point.
that seems like as hard as NP.
One
But
would, yeah.
since you have these 2 circuits, that's
I
maybe.
think, this is the problem.
Oh.
You have a very specific, like.
Yeah. And as you show, it can be like AC circuits are without loss of generality, like AC0 and almost NC0, and the.
like the second circuit can help you break the first circuit.
Sure. Yeah, I've never seen any work that does anything like this.
No, but stop her.
I don't know why you pick on the assumption. I mean, it's an algorithmic result. If reduction, if you have a polynomial time approximate Nash for 2 players, then you have PPAD in 2 to the root n.
Yeah, but she wants to know what to believe in.
What to believe?
This work was
We
done
don't.
There is
We
an
don't
if
have
anyway.
even with the real ETH, we don't know what to believe.
No, right. But you
Okay.
want
No,
to
we don't.
compare
I
them.
think- I know,
But
I
this
know
work
what I
was done
believe.
to convince
uh,
that
uh,
equilibrium is hard.
Okay,
Avi's right. I mean, it makes sense.
I'll give you another way of looking at this. Okay, I have some very good friends who were trying to prove an algorithm for epsilon Nash, like prove a p-test for Nash, like prove like a polynomial time. Okay. Now, if you're going to try to prove this, you better start by like understanding the circuit and showing that you can do something non-trivial with circuits. If you're just going to play with dimension reduction and whatnot, that's not going to work. Okay, so this is.
I see what you're saying. I'll give you I'll give you an example. Like if you want to factor a number, it's hard. But if you have two numbers, and you know that they have like a common.
Yeah. Of course.
It's easy, right? Somehow
Sure.
you can use one to break the other. So right.
That's fair again, but but I've never seen again like so you have like two black box circuits versus two white box circuits. Can you do better?
Yeah, there's a relation.
It's not black, but they can be computed in time like in size less than n squared.
Yeah. Yeah. No. Obviously, yeah. I'm not. Again, I'll be very excited if this will be
And you didn't see,
false.
I think, part of it because we don't have lower bounds. For all we know, everything can be computed
Yeah.
by n squared, so by size n squared or a little bit more than n. So yeah, it's hard to know if it's true or not.
Yeah, but definitely, I think it helps. If you're looking for an algorithm and playing with a utility or something is probably not the way to go.
Are there attempts to show that reductions won't face up to p-pad, or is it hopeless?
So p-pad is like there's issues like NP intersect co-NP and. And also they're like however convincing you find those, but they're like oracle separations. We know of those classes.
Yeah, I think like every server starts with like p-pad is in the intersection or something, and therefore you don't expect it to be NP hard or something.
That could be a result in a different way that shows that the complexity are polynomially related, but I don't know. What's the quantum complexity of end of the line?
I have no idea. I'm probably still hard.
Because it's
like
to the
yes,
omega. What is
Grover.
to the omega n?
Grover search.
No, I know you
it's
can,
to
but
the
that's in
omega.
the exponent. Grover search is. That's why I'm asking. Yeah, but that's
Yes.
I'm asking whether you can get a power of n. Nobody.
You're asking whether what?
Just whether
say
quantum
you can do better
result
than
you can do
polynomial?
2 to the n to the
0.99.
0.9.
Probably not no.
It's probably not. No, I'm wondering. I don't remember seeing it, but maybe
So why not
somebody else saw.
Grover? Why not?
Grover gives you just shaves a factor of 2 in the exponent. So it remains
Square root, but
omega
not
n.
in the higher
Oh,
place.
it's
Probably know
squared,
all the quantum
yeah.
algorithms.
I probably,
so
yeah,
just
that's
check,
right, yeah.
all
Two.
three of them.
Oh, there are three? I
So it
thought
will
we
be
had two.
extremely
What
interesting to have
are the
another
third one? And Shore
quantum
and-
another.
Sure, go there and then
Can,
there's another one.
Simon.
There's another
That
one?
is,
Simon is
quantum,
used in one of the
random
examples,
walk.
like
any
No,
more
Simon's is black box.
any more questions? Would it help you to have an NC0 expander on exponential?
I don't see.
What you
yeah.
We'll find a way to.
I know.
Yeah,
I know I have one. I could give him one. I could.
I have a compression. Can you use it?
I just in the beginning. Yeah. Okay.
The expanders here are very simple. You just
What you mean? Okay. All right. Thanks a lot.